Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Well, if I have 6 people and I want a group of 1, a group of 2 and a group of 3. Now I guess I wrote them in that order, but really I only care about the groups. I don't care about the order within the group. I care who is the single, who is the pair, and who is the triple. Can anyone give me a formula? You don't have to know the number offhand. A formula for how you might calculate that number of ways. You can start with something and then divide if you want. Or you can just use a... we've been talking about multinomial coefficients, and it is in fact a multinomial coefficient. So how many ways of dividing 6 people into a group of 1, of 2, and 3? Yep. Exactly, it's a multinomial coefficient. 6, choose 1, 2, 3. So now I just want to get into some of the subtleties that are associated with this. How many ways are there of dividing the same 6... Okay, well, this one's arguably even easier, into a group of 2 and a group of 4. Right, now, our 6 people have to be broken in a group of 2 and a group of 4. How many ways of doing that? Yeah, 2, 4. Now that, I guess you could call it a multinomial coefficient. That is, of course, the same thing as 6 choose 2. So, in other words, 6 times 5 over 2, 15. Okay. By the way, this one, we can, of course, calculate that using the normal formula. Remember that the bottom ones have to add up to 1 factorial, 2 factorial, 3 factorial. So, that's the same as this, except without the 4 factorial on the bottom. So I think it should be 60. Just by comparison with this, it's 4 times as large, in my view. But, so, that's not the key point that I'm making. The key point is... I'll get onto the document cover in 1 second once it's ready for me. Okay, let's divide the same 6 people into a group of 3 and a group of 3. How many ways are there to divide 6 people into 2 groups of 3? 6 choose 3. Yeah, which is of course the same as 6 3 3. Now, you'll probably be upset for me to say it depends on the exact phrasing of the question, unlike the previous ones. It's a bit more subtle. So what I said, okay, what this definitely is the number of ways of, there are a number of ways you can take a word, this is broadcasting my voice, so I have to modify the... I'll just talk a bit softer. What this definitely is the number of words. At the top line here, 6 choose 1, 2, 3. That's words in 6 letters, words in 3 letters, sorry, A, B, C, having 1 A, 2 Bs, and 3 Cs. So just remember, like, group A would be the 1-some, group B would be the 2-somes, group C would be the 3-some. You have to have 1 A, 2 Bs, and 3 Cs. It's a word of 6 letters. So in other words, the ways of breaking up 6 into the first group having 1, the second group having 2, and the third group having 3. Now, this is once again breaking up 6 into the first group having 2 and the second group having 4. So what this is the number of ways of breaking up 6 into group A and group B, if you like. I'll label them. Group A and group B. Group A having 3 members and group B having 3 members. That's what 6 choose 3 counts. And the question we have to answer, is that the same as breaking 6 into 2 groups of 3? Is that the same question? Okay, and if not, why not? I'm just not going to use A, B, and C for people because I'm using them for groups. So let's do them as words, right? So 1, 2, 3 in group A, and 4, 5, 6 in group B. So that would be the word A, B, B, B in the word interpretation. Yeah, each pair, each breaking up, each subdivision is counted twice. One where the first group is counted as group A, and one where the first group is counted as group B. This problem doesn't occur in the first two examples because you can identify a group by its size. Here, the groups are indistinct by size. There are two groups of size 3. It's not clear which one should be which. So, all it gives you is another factor. So this would be the number of divisions of 6 people into 3 in group A and 3 in group B. So that's the same thing. If I just want 3 in one group, 3 in another group, I don't care which one is A and which one is B. Each arrangement will be counted twice. Once with the first group as A and once with the first group as B. So I divide by 2, and I'm going to suggestively put 2 factorial, because whenever you have a whole number of larger units that can be rearranged among themselves, effectively that's another overcounting by a factorial. If there were 3 groups of 3, I'd divide not by 3, but by 3 factorial, because there would be groups A, B, and C, all of size 3, and then it wouldn't have mattered whether I labelled them ABC, ACB, BAC, BCA, CAB, CBA. All those 6 ways of labelling the 3 groups would have meant the same thing. So in addition to you see this already has factorials on the bottom. That's for permuting within a group. There's an additional factorial on the bottom that is for permuting the groups themselves. So this is an important thing to bear in mind. So I'm going to move to the document camera. And we can do some more complicated examples of that nature. So just to summarise what we did a moment ago, and I'd better get these lights down. 6 into group of 2 and group of 4. There are 6 choose 2 4 ways, just to match the multinomial coefficient off of that. And the more subtle case we had was group of 3 and group of 3. And I'll make it more explicit, the question, because I said it depends a bit on the phrasing. I don't care which group is which. I just care that there are 2 groups. Don't care which group is which. So the labelling of the groups doesn't matter. 6 choose 3. Sorry, I could have of course just said 6 choose 3, but then I have to divide by 2 factorial. And the way to think about that is to permute the group labels. The group labels typically have letters if you think of the word letter interpretation of multinomial coefficients, and if you permute those letters you get the same assignment. That's what it means. What if I were to take 10 and I want it's probably these ones. I don't know why. I'll just talk softer. Okay, so let's say it's some kind of game and I have to... Does anyone remember what I did did this last time? Lectin my... What about program audio? Program audio? Is that better? I hope so. It's a game where we have to allocate 10 players among... I have to allocate 10 players, a king and then three courts for the king, some kind of medieval themed game. So, but I don't really care which court is which. I just have 3 courtiers, 3 courtiers in each court for the king. Yes. So, once again, a counting problem. How many ways can you do this? Suggestions? Multinomial coefficients are a good starting point, and I won't even ask you to evaluate the multinomial coefficient. Of course, the title of this would always be how many ways. That's what combinatorics is, how many ways. Yep. Now, you've taken advantage of a little convention that there was, that you're allowed to omit the last one if it makes it add up to... Because a more formal thing would always include all of the things that add up to 10, but if the last one is missing, we just count that as an extra group. I'm going to put it in there. So 1 is clearly the king. That can be identified by the group size, but the 3 that are here can't be identified by group size, and I didn't care which court was which. They might be travelling. I just care who is in which's court. Like, as a group, the relationships among people matter, but which group is labelled A, B or C does not matter. So this is not yet the correct answer. I have to... Yep, once again, and of course that was permute group labels, A, B, C. That was actually A, B. So permute court labels. Okay. So with a flawless segue, I'm now going to continue with the court theme and have a tournament, a tennis tournament, and it's doubles. We only do the doubles, and let's say it is a single-sex tennis tournament, because of course mixed doubles introduces a whole new complication. Actually, mixed doubles might make it simpler, because then you always have a man and a woman. So let's make it more complicated by having a single-sex doubles tennis tournament. And I want to know... Now, we could go all out and have 7 rounds, but I'm not going to do that. I'm just going to do the first round. Everyone plays each other. Can you see this? So the first round, how many players do I have? Let's just say I have 8 players, so this is a very small tournament. There's only going to be two matches in the first round and 1 match in the second round. So that's a short tournament. The principle generalises. Okay, how many... Okay, first round's possible. Now, of course, the final is determined by the outcome of the first round, so we don't have to schedule that. We only have to schedule the first round. Rosters or allocations are possible. Okay? Now, it goes without saying, well, it's a matter of interpretation once again, as always, but the roster is not particularly, if you read a tennis roster, it doesn't say, what you care about is not, this person was allocated to Margaret Court Arena on the north side and on the left of the pair. That's not how it works. You just say, Williams and Williams against, Harlequin. I don't know who is currently playing doubles, but, you only care about the pairs, the players. You care about which pair is which. You care about which pair plays which pair, but you don't care about incidental details like which court they're on, that kind of thing. So how many first-round allocations are possible? Let's start. It's always good to start by overcounting, especially if it's going to be overcounting by a consistent factor. So a way of overcounting would be to be hyperspecific in ways that we don't want to be hyperspecific. Eight is an easy thing to start with. And there's actually many ways you can get to this answer, but there would be... So, yeah. Well, let's start by doing it with the 8-2-2-2-2. You could also start with 8-4-4, because that would decide who was on which court first. But let's do it by doing 8-2-2-2-2. So that specifically has found 8, and it's divided into 4 pairs. I'm going to label them pair A, pair B, pair C, and pair D. Now remember, the multinomial coefficient has only accounted for the fact you can swap within the pair. It has not accounted for the fact of swapping pair A with pair B and relabeling A as B and B as A. It has not accounted for that. So I don't particularly... So now that's how I get the pairs. So far so good. Now I have to allocate the pairs to 2 quarts. Yeah? Arguably A, B, C, D. That would be one first round. Now we just have to think of how many actual different allocations are there. There are 3 essentially different allocations. So once you have it down to just 4, so first of all, so that's with specific named pairs. So now let's divide, sorry, you'll forgive my annotations, you can ignore pair A, pair B, pair C, pair D. So it's just this number, which is the number of ways of doing it that way. Now, for the moment, let's consider all the pairs interchangeable. So that would be divided by 4 factorial, because there are 4 pairs. That's relabeling the pairs. But unfortunately, that's not quite the right answer yet, because A versus B is different from A versus C, which is different from A versus D. But those are actually the only 3 options, because once you have A versus B, you know it's C versus C. So it's 3 times this. So now, that's not to say it's the only option, and a good exercise would be to do it by 8 choose 4, and then proceed from that point. You should get the same answer. So that's probably enough of more complicated combinatorics, but you can see it's more than just multinomial coefficients. It's about that principle of figuring out how many times you've overcounted, and that's when it's every counting has been overcounted the same way. If it's mutually exclusive, you know you don't multiply, you add instead. So I just want to record for the record that the advanced controls, which might save me from this problem, require a pin, naturally. So let's go on. Okay, lattice paths. This is another good one. Oh, so we're going to do lattice paths, and this is where we were up to in the combinatorics notes that you would have seen. So before I go on with lattice paths, I actually just want to elaborate on the number of pairings. Sorry. Pairing, which means perfect matchings. This is just an extension of the tennis court thing we just did of 2n objects, okay, or they could be people. Now, a pairing means how do you pair them up? It doesn't mean I care pair A is paired different from pair B or pair C or pair D. So we're going to start with a multinomial coefficient, 2n. What do I put down the bottom of the multinomial coefficient? We want to divide the 2n into groups. Another way of doing that is doing a word in 2n elements where the letter tells you what group that person is in. So it could be A, B, A, which means person 1 in group A, person 2 in group B, person 3 in group A. Now, each group is a pair, so, you know, a perfect matching means they should be all paired up, much like, you know, domino tiling. It's actually a non-trivial field of maths to actually figure out about all these domino tilings. But, you know, as far as a perfect matching goes, they don't have to be next to each other. So just any ways of pairing them up. But I don't care which, I don't care the labels of the pairs. So pair A has 2 elements in it, right? So, Okay, so there are n pairs. Okay, so there are n 2s down the bottom. But this is not yet the correct. I have to divide by something. So if I just had this multinomial coefficient, it wouldn't be the number of pairings per se. Can someone describe in words what it would be? Well, I want the pairs to be distinct anyway. I don't want them to overlap. Yeah. A good word to use sometimes is labelled or identified. So you could call it a labelled pairing, because this says that group A has to have 2 in it. So that's a labelled pairing of 2n elements into one pair labelled A, one pair labelled B, and so on. So that's clearly over-counted the correct number of pairings, because the pairing where this is called A and that's called B should be the same pairing as where this is called B and that's called A. So we divide by the total number of ways of permuting the pairs among themselves. How many pairs are there? N. So it's 1 over n factorial times this. It's the number of perfect matchings. Okay. Now, that doesn't have... So the reason I put a cross through this is that there's no topology involved. I'm not saying it can only go to its neighbour or anything like that, so that was a misleading picture. In particular, if I had 6 people on a circle, this pairing would certainly allow pairings where there's crossover. So there's nothing claimed about the topology that they don't cross over. Later, maybe I'll answer the question where you say they can't cross over. That's a slightly different question. Okay. So that pairing is also okay, as is this pairing. So that's in this. Okay. So we'll get back to pairings a bit later. Now let's move on to lattice paths. Now, if you talk about all paths from P to Q, it's actually a tantalising question. It gets towards things called self-avoiding walk and this kind of thing. If you just want a path in the lattice that doesn't touch itself, it's a very difficult question. It's actually regarded as an unsolved statistical physics question, how to analyse self-avoiding walk. It's not known. So we do a simpler question to make it more tractable, and the simpler question is still a path that doesn't touch itself, but it can never backtrack, so never go left and never go down. It starts at the bottom left and goes to the top right, and it should never, ever go back by going left or go back by going down. And how many ways can you do that? Well, okay, it's easy to read. Each path must go up exactly 3 times and right exactly 4 times in any order. So you see the word interpretation is very powerful. So arguably sometimes, well, both of them are equally important, but the interpretation of a binomial coefficient as a word in 2 letters, or a number of words in 2 letters, and multinomial coefficient, the number of words in k letters, is a very important interpretation. Because here, how do you encode a path? Just tell a robot how to do it. Right, up, right, up, right. Every word is a valid path, so long as it has 4 rights and 3 ups. And every path translates to a word with 4 rights and 3 ups. So it's a perfect bijection. And yeah, it's 7 choose 3. So yeah, in general, if it's P by Q, then it would be P plus Q choose P is the number of paths. And now that they're proving some basic identities by saying every path must go through either this point or this point. So that's one way you can prove it. So every path from here to here must either be a path from P to, I'll call it Q1 here. It must either be a path from P to Q1, then followed by going right, or a path from P to Q2, followed by going up. Those are the only 2 possibilities, because you can only go right or up. And the paths from P to Q1 is 6 choose 3. Paths from P to Q2, so that's Q1, and the paths through Q2 are 6 choose 2. So you just add them up, and that's a 1-to-1 bijection, 1-to-1 correspondence with the set of all paths of length 7 with 4 rights and 3 ups. So you're dividing according to the last step. You could easily have divided according to the first step, and you would have got the same subdivision. So yeah, but you could even think about this without talking about lattice paths. It's quite easy, because I've got this is a better way. If you do want to remember the identity, I'm not even sure whether it's worth remembering it, but if you do want to remember it, you know, I've got m plus 1 objects, so just call the one object a special object. I want to choose k of them. Either the special object is not in it, then you're choosing k from the m non-special objects. You know, so you've got, you know, m blue objects and one special red object, then either you could have k that are all blue, or you could have the one red object and then only k minus 1 that are blue. So you don't have to do it through lattice paths. That's one way to do it. Pascal's identity can be proved algebraically. Now, this would have to be the most tedious thing ever, especially when the algebra only exists to serve counting, so I wouldn't recommend that. That's kind of a last resort. Okay, and note 2 is exactly what I just said. Van der Monde identity. Okay, yeah, naturally it can be proved using lattice paths, but yeah, but the simplest proof, indeed, you can talk about committees, or you can just think, yeah, men and women, choose k of them. By the way, this there's actually something called the hypergeometric probability distribution, and I think we'll even do it later. Okay, because the hypergeometric probability distribution, we haven't really talked about distributions, but if I have m men and w women, and I pick a committee uniformly at random, the question is, how many women does it have? Or men. You could do it either way around. And if you were selecting independently, then this would be a binomial, right? Is the first person woman, yes or no? Is the second person woman, yes or no? And add all those up. Because they're not independent, you have to, you know, once you've selected one man, there's fewer men in the later. So once you've selected a man, the chance of selecting a man in subsequent selections from the same group goes down because there are fewer men left. So it's not actually a binomial. In some kind of high m and n limit, it approximates a binomial. Anyway, the hypergeometric probability distribution says the probability that, you know, we haven't even done distributions yet, but since you've done a first-year statistics course, you may not have seen this distribution. The chance of the random number of men that you pick being m, where n is the number of men picked in a random, I'll call it a K committee, meaning a committee with K attendees. So little n will be smaller than m because m is the total number of men and w is the total number of women. So it's just, once again, you have to choose n men from the men, and from the women you have to choose k minus n women. That's the chance, divided by the total number of committees is, of course, sex blind. If you want the total number of committees, you just have men plus women, choose k. So of all that total number of committees, all of which are equally likely, this is the number that have exactly n men. Sorry. So anyway, might get back to that later, but it follows straight from this. That's the only reason it's mentioned. And very clearly, so Van der Monde's identity, there's a lot of things named after Van der Monde, so let's just call it the identity related to the hypergeometric distribution. That's saying nothing other than that all these probabilities of different n values, they all add up to 1. Which, you know, you have to have some number of men. That number of men will be between 0 and k and possibly smaller. Okay, so lattice paths is not the greatest way to do that. Yeah. By the way, a little convention is that if you ever have, I think this convention is worth even writing. If in n choose r, if r is a integer, okay. So by the way, I don't know whether people use double-barreled notation so much. So I will be using this sometimes to mean the set of all integers. Okay, whole numbers. Set of all integers, because it saves me writing out r is a whole number. And r is less than 0. So we know that, what is n choose 0, by the way? It's 1, it's not 0. Because there's one way to choose nothing, it's the empty set. That's one way. But if r is less than 0, then n choose r. What do people reckon it should be? What's the number of ways of choosing, for instance, -1 elements from n? Yeah, there are no ways of choosing it. It's 0. Whereas there is one way of choosing 0 elements. That's the empty set. So n choose 0 is 1. But if r is -1 or -2, then this is 0. But also by symmetry, we've got that nice symmetry for the binomial coefficient. So just by the same way, we should say if r is strictly greater than n. If I have n elements and I want to choose n plus 1, I should have 0 ways of doing that. So this is arguably a convention, but it's a very useful convention. And to read this most precisely, you need to use that convention. But for instance, you might have 3 men and you want a committee of 5. So 3 men choose 5. What does that mean? It's 0. And it's totally true. The identity is absolutely true, but you have to use this convention. So it's possible. And likewise, the decreasing by 1 could have the same issue. Okay, so sample point method. It could be impractical, you don't say. Okay, so even with assistance from combinatorics. So combinatorics is a little bit better than the plain sample point method because you're saying that each of the things is equally likely and you have some complicated method to count the number of favourable outcomes and the number of unfavourable outcomes. So we go on to find more ways of finding probabilities. And this is where I say we do a bit of a phase change back from combinatorics, which is about clever ways of counting things, back to probability, which is more about composing events. While I do really want to go immediately to do that, I can't help but fulfill the advertised thing about pairings. So what about pairings of n points on a circle that don't overlap. So I'm sort of focusing on that kind of thing. And of course, you might draw things so that they cross. I could have drawn those connections so that they cross. So it can be made to not cross. Actually, because it's a bit simplifying to talk on a circle, because if you do straight lines within a circle, if they can be made to not cross, then they won't cross, because straight lines only cross if they're... that's a little... So, on a circle, so for instance, this is a, Now, sometimes these are called rainbow patterns. Now, that doesn't look much like a rainbow. But if I just pick an arbitrary cut point, if I just put my scissors here and I cut, if I cut the circle at that point and sort of write everything out on a line, then I'm now going to have to bend my connections. So this is now the far left, that goes all the way over to the far right. The second from left goes over to second from right, and then I have two like this. So you can see why they're called rainbow patterns, although it's not like any rainbow that I've ever seen. They have this nested property that and I should say 2n. So not so easy to pair if it's odd. So let's say number of pairings of 2n points on a circle that do not cross on the circle. If you're doing it on a straight line, then let's say they can be made to not cross by drawing those lines. Now clearly this is not every pairing, because here's a pairing that cannot be made to not cross. Whether you do it on a circle or like this, it's just, that is disallowed. Okay? So we want to know the number of ways of doing this. And I just love doing this because we did just talk about lattice paths, and I want to make them useful for something. There's an incredible way to do this using lattice paths. So let's think about it this way. So when you write it, by the way, another way is bracketing. So if anyone's done any, it's also, anyone who's done any computer science will know that, or even worked with R, balanced bracketing is essential. And the number of balanced bracketings of n open brackets and n closed brackets, well, not only is it related, I can find a simple bijection, which is if I'm opening a bracket, then I start a pairing. Right? Each bracket is open bracket is paired with its closed bracket. I don't need to annotate on this diagram which one is the open bracket and which one is the closed bracket, because the first of the two must be the open bracket and the latter of the two must be the closed bracket. So I have an open bracket here and a closed bracket here, and those are paired. That's why it's a balanced bracketing. This bracket matches that bracket. Now within that I have another pairing, open and closed, and then I have so if you're ever doing a computer language, you'll have things like this. Lisp especially, but any computer language. So, so what is totally... now, it's funny, it seems like this is disallowed, but the corresponding bracketing is not disallowed. Open, open, close, close. That's not disallowed, but it just means something different, right? The meaning of that, if you look at the bijection, even if you tried to do the bijection from this and got that, when you map the bijection back, you wouldn't get the same thing. You would get this balanced pairing that doesn't cross itself. Because there's no way you would match that bracket with that one, you'd match it with this one. So the balanced bracketing comes naturally from the fact that you close the most recent unclosed bracket. That means that you connect to the most recent unconnected pairing. That ensures that you never cross. Because if you always do the most recent one, there's no way to ever cross. So that is a, so there is a bijection between that and that. And balanced bracketings are good, because we talked about words in the letters up and right, or words in the letters U and R, where U is R. Let's just imagine that each open bracket is a U, and each closed bracket is an R. Okay? So balanced bracketings is like that. So these are words, but they're not all words in U and R, such that I told you the lattice path would come up. You see, I didn't want to be too critical of lattice paths, but I want to save them for a context where they're really actually useful, such that the lattice path, let's think what this lattice path does. You have, well, number one, it's in a square, so that didn't look too square, but I'll just have a funny aspect ratio. So I have to do, so here's my square. It's four brackets, so there'll be 4 ups and 4 rights, but it's not any such path. There is a constraint. Does anyone think of a geometric way of describing that constraint? You'll have to speak up if you want me to hear me. Well, first of all, could the first one be an R? Is that allowed? Or could the first one be a closed bracket? Not allowed to be a closed bracket because there's nothing to close. In other words, it has to be the start of a pairing, the first one, not the right. So it has to be a U. So the first step must be up. Now the second step, it could be up or it could be right. In this case, it's up. In this case, it's up. In this case, it's right. That closes a bracket. And then we go up again, which opens another bracket. Okay. So here's one way to think about it. Clearly every balanced bracketing, or every pairing like that, gives us a word. Easy, you just do go up or right. Given a word in U and R, it's got to have four U's and 4 R's. What is the one criterion that would tell us that it's become illegitimate, that it's not a legal bracketing? How would your editor tell you that you've messed up your bracketing? If it's only open brackets and closed brackets, there's only one thing that could go wrong.
Starts with R or N.
It's a slightly more generalized version of that, because, and let's say a more complicated question, yeah, it would be bad to end with U, but if you've only read up to a certain point, let's say I've only read up to a certain point, I can't quite tell because that might, in the end get back to the start. So the real thing that would be problematic, if I have U at the end, that would be like an open bracket. Maybe I'll close it later. But what would be really bad is if I have a closed bracket and there's nothing to close. And if you think about it, if you're reading progressively, that's really the only thing that can go wrong. So long as you have the same number of opens as closed, that will fix the problem that you talked about at the end. It's not possible to have a U at the end. If you think about a U at the end, how could that happen if you had 4 opens and closes, 4 closes? That must have happened if you closed too many times before. So that's the only way it could happen. So the only thing that can really go wrong is if you close too many times, which corresponds to having more R's up to a point than use. More closed brackets up to a certain point than use. And if you think about that, that's going to the right of this line, y equals x. Okay, so this is where the kind of geometrical pairing. If you touch the line, that's okay. That's having closed all the brackets that you've opened so far. If you go to the right of the line, not okay. Okay? Not okay. So here is a... I don't have that much time, so I'm going to do it very quickly just to get you the formula. So the number of... so this is a bijection with the number of paths from 0 to 0 to n, right and up only, and stay above the line, above greater than or equal to the line y equals x. Okay? So this is the nice bijection we've got for lattice paths, that they have to stay above or on greater than or equal to the line y equals x. That is what we're measuring. Now, the last part of that is tricky, so I'm going to do it very quickly, but trying to figure out exactly how many paths there are that do that is hard. So just like before, it's easy to... A path that stays above the line y equals x... oh, wait. Okay, I'm going to do it this way. I'm actually going to have n, and then this will be the height y equals n plus 1. So I'll have an n plus 1 by n box. So it will be n plus 1 high and n across. So once again, there's this line y equals x. So staying above the line y equals x, that's actually the same. Okay, sorry about that. Okay, essentially, at this point, this is extension, so the exact proof will not be examinable. But I want to finish this since I've opened with it. So this is x equals n plus 1. So yes, I did mean to make it n plus 1 across and n high. So if you stay above the line y equals x, that's the same as staying above the diagonal of... Clearly, if you stay above y equals x, you stay above the diagonal of this n by n plus 1 square. So the bijection is to paths 0, 0 to x equals n plus 1, y equals n, and ru only. And also they have to stay above the diagonal. The diagonal is no longer y equals x. Okay? So that's the same path, but with an extra r at the end. You put an extra r, you have your path, it somehow gets here, and then you just put an extra r at the end. That's the same bijection. You might think, why, if it stays above this diagonal, why does it stay above that diagonal? That's a little thing that you can check if you like. And such paths, now there are 2n plus 1, choose n, such paths without the constraint star. Star is the constraint that they stay above the diagonal. And here is the amazing thing. Of those paths, now you might say, why did I go from a square to a rectangle? Well, to get the right answer, it's actually a famous formula once we get to it. To get the right answer, I want a way of what works with the rectangle n plus 1 by n that does not work with the square, is that each path has a way. If I just think of paths in L in R and U, right and up, paths in right and up, they're words in R and U. How do I get another path in R and U? Well, one way is just cyclic permutation. I mean, by the way, any permutation will take R's and U's to R's and U's. But cyclic permutations are of particular interest because cyclic permutations do something interesting to the property of staying above the diagonal. So if you stay above the diagonal, it turns out any cyclic permutation, a cyclic permutation consists of, moving everything a certain amount to the right and taking the n bits to the start. So if you're moving from here all you have to do to check whether it stays above the diagonal from here, the cyclic permutation is like starting here, and then clearly there'll be at least one point that is below it. So if I take, so only one of the 2n plus 1 cyclic permutations of each word in n u's and n plus 1 r's, because I have to have n ups, n plus 1 r's, only one of each one of those 2n plus 1 cyclic permutations stays above the diagonal. Because if two did such, then they would have to, you'd have to have 2 points such that it sort of lies on the diagonal. Effectively, it would have to lie on the diagonal. And it's a fact that no points other than the start and the end point lie on the diagonal because they're co-prime. There's no common factor to n and n plus 1. So it's a little bit of a complicated argument, which is why I describe it as extension. So the number is 2n plus 1, choose n, divided by 2n plus 1. This is the number of non-crossing pairings, which we talked about at the start of this thing. And it's also called the Catalan number. So if you've ever heard about the Catalan number, this starts whole courses in combinatorics. And I think that's an appropriate point to end our discussion of combinatorics for this. I don't expect you to know so sometimes this is called Cn. 2n plus 1 choose n over n plus 2n plus 1.